Hi everyone, welcome to my series of videos on complex analysis, covering complex numbers, complex functions, analytic functions, checking for analyticity, all that good stuff. Starting off with introduction to complex numbers and complex plane. So just as a warning, or I guess a PSA, you will need some knowledge of calculus and trigonometry going through this series. For the first couple of videos, you will get by with some basic algebraic knowledge while dealing with just addition, subtraction, multiplication, division of complex numbers. But later on, you will definitely need some basic trig knowledge, and later on definitely trig and definitely calculus knowledge. But anyone is welcome to watch the first couple of videos on the complex number and the complex plane. So to understand the complex number, I'd like to first just kind of remind ourselves what real numbers are like and how they work, and from there on we can move on to the complex numbers. So real numbers are numbers. I'm actually going to do this fancy thing of set of real numbers. They are numbers such as, say, -1, 0, 1, 2, 3, 5, 8, 13, so on to infinity. Actually, in infinity, to infinity in both directions. Also, any decimal numbers, both rational and irrational. So numbers like 0.123, which would be a rational number, or a number like pi, which is 3.14159, and so on. It goes on to infinity, and it cannot be represented by a fraction, so that's an irrational number. But that's all real numbers. To represent these numbers graphically, we can use an axis with some markings on it. So here we'd have the origin 0. We would mark negative numbers on the left side of 0 and positive numbers on the right side. Here are the integers, 0, 1, 2, 3. Whole numbers that would include -1 and 0, I believe. Don't judge me. Rational and irrational numbers such as 0.1 to 3 would live between integers, and 3.14 number pi would live somewhere here. So there's the pi. Here's 123 over 1000. Alright, so these are the real numbers. Imagine you had some variable v, not v, let's call it x. Alright, and you were putting different real numbers into x, and you wanted to plot them. So let's say x equal to 2. So we'd have 0 here, 1, 2. Here's our number 2. If x equal to 3, 1, 2, 3. Here's our new x. Alright, we call it x-axis. Here is, on this axis, is where we put numbers that onto which x takes. Alright, we can have another axis here, say a y-axis. It's a different variable. It can also take on different values of real numbers, such as, well, let's go with 0. Here's 1. Y can also be 1.25. Place it right here, and so on. Now, here's something that is real basic, but you're going to see why I'm mentioning this. When we're adding real numbers, we just go along the scale here, along this axis. So if we had a number 1, 2, 3, 4, if we had a number 1 and we added 2 to it, so we go 2 over like this to number 3. So this is our original, this is our answer. So all these numbers lie on the axis. Alright, and this is going to contrast with the way that complex numbers work later in the video. All right. Now, a quick reminder for those who did not know or who forgot what an imaginary number I is. Imaginary number I is a solution to this equation. X squared equals to -1. Usually we cannot square things and get a negative number. However, number I is a construct that allows us to perform this kind of math, and it's extremely useful in a multitude areas of science and math. So, we just went with it. So, as you see, when we plug in a number I in here and square it, we will get -1. And because of that, number I is defined to be the square root of -1. All right. Now I is a number, just like 2 or 3. So in the sense that you can do math with it just like with real numbers. All right. So we can have 3 multiplied by I gives us 3i, and so on. We can have 2i plus 3i gives us 5i. So it works a lot like the real numbers. So we can say 2i times 3i, we will get 6i squared. But hey, I squared is -1. So it's going to be 6 times -1, which equals to -6. Fantastic. So that's what number I is. That's how it works. Now we can also have an axis where we would plot our I values. All right, so this would be 0i, this would be 1i, 2i, 3i. We can also have fractions of I, say 2/3 I would be right here. And again, any rational or irrational amount of I, we can have pi I. All right, so it works just the same when it comes to an axis. Now, something you probably come across before is putting axes of real numbers together perpendicularly and obtaining a coordinate plane. This coordinate plane is made up of x-axis and y-axis, and both x and y are real numbers. So if we happen to have an x value of 4 and a y value of 5, here's where x would be equal to 4 on just the axis itself. On the x-axis, this would be 1, 2, 3, 4. So 4 is located on the y-axis itself, out of context of coordinate plane. Y equals to 5 would be 1, 2, 3, 4, 5 would be right here. All right. But once I put these two axes together in this new context, now these two map to a point in the plane. So this is point in a coordinate plane. All right. And this point has the coordinates of 4, 5. This tells us how to get to this point by using these two axes. Go 4 in x direction, go up 5 in y direction, you've got yourself a point. All right. This, however, is not a number. This is a point. These are numbers, the real numbers on the axes. Now, if you happen to put an x-axis and an y-axis together, you'll get something very similar with a very small difference. Well, I guess it's major, but it's not too different. So what if you had an y-axis, which, let me call it imaginary, and you had a real axis with real numbers? And if we went 4 in the real direction and 1, 2, 3, 4, 5 in the imaginary direction, this would map you again to this point in the plane. However, the difference is that now this point is also a number, and it's the complex number. Complex number z. And it would be equal to 4, 5. All right, so it again is a point on a plane, but at the same time, it is now a number which has two parts to define it. Before, we only needed, if you can see this, we only needed one number to define a number, basically. But now we need two real numbers to define a complex number. And I'm going over 10 minutes, so I'm going to continue in a different video. See you next video.